Welcome back to the class on power semi-conductor trace. In this class, we are going to discuss about some of the numericals based upon the DC drive. Now, let me take up the first numerical. The speed of a 150 HP 650 volts 1700 rpm separately excited DC motor is controlled by three-phase fully controlled converter. The converter is operated from the three-phase supply, 460 volts and 50 Hz supply. The rated armature current of the motor is 170 amperes. The motor parameters: armature resistance equal to 0.099 ohms, armature inductance equal to LA equal to 0.73 millihenries, and the motor constant Ka equal to 0.33 volt per RPM. Neglect the losses in a converter. Determine the following parameters. The no load speed at a firing angle alpha equal to 0 and alpha equal 30 degrees. Assume that at no load, the armature current is 10% of the rated current. So this is the circuit diagram. This is the separately excited motor. So what are the parameters are given in the numerical that we have written here? These parameters are related to the output. These are the parameters are related to the input supply. 460 volts is nothing but a line to line voltage. Whenever the input voltage is given, that is always given the line to line voltage 50 Hz supply. At no load, we have to calculate the speed of a motor. So at no load, the armature voltage, all the voltage given by this converter, that is VA equal to root 3 VML by pi cos alpha. Suppose if you take alpha equal to 0, nothing but it gives the maximum voltage. So you take alpha equal to 0, substitute all the values, VML, maximum line voltage. This is the RMS line voltage that we have to multiply with root 2. That gives the maximum line voltage. We are getting the armature voltage 621.22 volts. Now in this case, you have to calculate what is the back EMF. The back EMF equal to, if you apply the KVL in this two, the back EMF at no load equal to armature voltage, this voltage minus armature resistance. So already you have taken this voltage 621.22 minus armature current. It is given in the problem that 10% is rated current. Rated current is 170 amperes. So 10% means 17 amperes. This is the armature resistance. If you solve this one, you are getting the 619.535 volts. Now here the motor constant is given 0.33 volts per RPM. Suppose if you want to get the voltage, how much voltage? The voltage is highly depending on speed. So we have to multiply this constant with a speed in RPM. In any problem, if this type of constants are given, then you have to observe whether this speed in RPM or radians per second. Based upon that, you have to multiply that one. No load speed at alpha equal to 0, because the back EMF equal to no load speed into Ka. So no load speed equal to back EMF by constant that we have given the 619.535 divided by 0.33, 1877.37 RPM. How much speed the motor will be running if you take the firing angle alpha equal 30 degrees means again you have to calculate the armature voltage. This is the voltage given by the converter with the firing angle alpha equal to 0 degrees. That you have to multiply with the cos 30. It gives the voltage at a firing angle 30 degrees. You are getting the armature voltage 537.99 volts. Again, you have to calculate the back EMF. This voltage minus armature resistance drop. Armature current in the problem, it is given as a 10%. So 17 into 0.99. We're getting the 536.30 volts. So no load speed means this voltage divided by the constant that is given in the problem, that is 0.33. So it gives the speed of 1625.1 RPM. This is the no load speed of a motor when you maintain the firing angle alpha equal to 0. This is the no load speed of a motor when you maintain the firing angle alpha equal to 30 degrees. This value will be lesser when compared to this value. In second bit, the firing angle to obtain the rated speed of 1750 RPM of rated motor current, also compute the supply power factor. At a full load, first you have to calculate the back EMF. So rated speed is given 1750. 1750 into this value already given in the RPM. So you have to multiply with the constant of the motor which is given in the problem, so that we are getting the 577.5 volts. VA equal to EB plus IRE. Substitute all the values. Here it is given the rated current, so you have to take 170 amperes. You're getting the 594.44 volts. Output power. Output power equals voltage into armature current. Already given the 170 volts. Armature voltage also we found here 594.33. Substitute all the values. We are getting the 101.036 kilowatt of power will be given by the. This is the supply RMS current, because we have to calculate the apparent power given by the supply to the converter. Formula square root of IA square into 2 pi by 3 into pi. Pi gets cancelled. Finally, we are getting the IA into IA root 2 by 3. IA is nothing but a rated armature current that substitute here, and if you find the value 138 amperes. Already we calculated the output power. Now we have to find out the input power. So this value divided by the root 3 VL IL input power. VL is nothing but a input line voltage. IL is nothing but a input line current. This is the input line current. The input line voltage is already given in the problem. Substitute all the values. We are getting the 0.9189 power factor lag. Next, speed regulation for the firing angle obtained in a part B. Just now we have calculated the part B section where we calculated what is the input power factor of a converter. The speed regulation. Full load current is 170 amperes. That is given in the problem. 10% of the full load current, that is no load current. That is 17 amperes. EB at 10% of the IA, we are getting the VA minus, this is the rated voltage, minus IA naught 0.099. We are getting the 592.65 volts. Now speed of a motor at no load with this amount of voltage. So this voltage divided by the motor constant, it gives the 1795.91 rpm. Next, speed regulation. Speed regulation is nothing but this speed, no load speed minus full load speed. Already in the problem it is given that the full load speed is 1750. The no load speed minus full load speed divided by the full load speed gives the 2.62%. Next, second numerical. A separately excited DC motor having a speed of 10 HP motor, 330 volts, 600 RPM is controlled by three-phase fully controlled converter. Has a armature resistance 0.4 ohms, field resistance also given 150 ohms with star connected supply voltage PS equal to 220 volts, F equal to 50 Hz. The motor voltage constant, it is given as a 1.4 volt amperes per radians per second. Nothing but previously the motor constant is given as a volts per rpm, but here volts ampere radians per second. Nothing but to get the voltage, to multiply this quantity with a field current as well as the speed of a motor in a radians per second also. The armature field current is a continuous ripple. So here the input is the ABC voltage. This is the fully controlled converter. This is the motor. Parameters which are related to the field winding. These are the parameters which are related to the supply. Where the supply is connected, star connected. What is the voltage given here? That is the line to line voltage only. This frequency is 50 Hz. The line to line voltage is given at 220 volts. Given data, the armature resistance is given 0.4 ohms. The field resistance is given RF equal to 150 ohms. The supply voltage is given. Here we are going to find out the phase voltage. So 220 by root 3 ohms. We are getting 127.01 volts. We have to represent the speed of a motor is given 600 RPM. Rated speed that we are converted into radians per second. So we have to multiply the 2 pi by 60. We are getting the 62.83 radians per second because the motor constant is given in terms of radians per second. The firing angle, the field current is operated at its field current. The torque developed T equal to 120 Newton meter having a speed of 600 rpm. This is the first objective what we have to find out here. Here the field circuit also fully controlled converter is used. So the maximum field current is passing through the field winding. If you maintain the firing angle alpha F equal to 0 degree, so it is also three-phase fully controlled converter, the converter which is used in a field circuit. So VF equal to root 3 VML by pi cos alpha F. Substitute all the values. We are getting the field voltage given by the three-phase fully controlled converter, that is 297.08 volts. Now the field current equal to that voltage by resistance. This resistance value is given in the problem, that is 150 ohms. We are getting 1.98 amperes. Now you have to calculate the current. Current equal to torque divided by the KF into IF. So here KF value is already given in the numerical, that is 1.4. We found the IF value 1.98. This torque is given 120. So we are getting the armature current with this value of torque. We are getting the 43.29 amperes. Now the back EMF equal to the constant of the motor is given, that is volts per ampere radians per second. So we have to multiply with this constant with the current as well as the speed of a motor in radians per second. Just now we found the value rated armature current, nothing but with this value of low torque, how much is the armature current? You take this value here, 174.16 volts. Now we are going to find out the armature voltage VA equal to EB plus IA into RA. Substitute all the values. You substitute this value here. Our IA value we know. The RA value also given in the numerical. You substitute 191.48 volts. This is the armature voltage. Now how much, this much of armature voltage given, what is the firing angle that you have to calculate? So this voltage equal to, root 3 VML by pi cos alpha. VML is given. That is 220 into 1.414. Substitute all the values and find out the value of alpha. You are getting the alpha value 49.87 degrees. Next, the speed if the firing angle of armature alpha equal to 0 and the torque developed is T equal to 20 Newton meter. The firing angle of the armature converter equal to, again you have to use the same formula root 3 VML by pi cos alpha. In place of alpha A, substitute this value. So substitute all the values, we are getting the 297.08 volts. Now the back EMF at this value equal to VA minus IA into RA. Substitute all the values, we are getting the back EMF equal to 297.76 volts. Now the speed of the motor equal to this voltage divided by the KT into IF. So we are getting the value 100.92 radians per second. So that way, if we convert into the RPM means you are getting the 963.7 RPM. So third one is the firing angle of the field converter. The speed is increased to 1200 RPM for the same condition which are specified in the part B. What are the conditions are specified in part B? Same conditions, but how much firing angle of the field converter to get the speed of a 1200 RPM. The speed is increased to 1200 RPM. Again, you convert this value into radians per second. So we are going to multiply the 2 pi by 60, you are getting 125.6 radians per second. The back EMF equal to, once we know the speed, you can able to calculate the back EMF. So back EMF equal to the motor constant into IF into NF. But we have to find out the IF value. We know the back EMF. Already we calculate the back EMF, that is here, because there is no change in the conditions in B. So you can take the same back EMF, that is 297.76. Here, find out the field current. If you find the field current, you will get the 1.59 amperes. So the voltage applied to the field winding, that is equal to IF into RF. We know the IF value and RF value is given in the numerical, that is 150 ohms. So we are getting a 238.53 volts. Now you have to find how much firing angle we are maintaining for the converter which is giving a power to the field circuit. So this voltage equal to 23 VML by pi cos alpha F, where alpha F is nothing but the firing angle of the converter which we are using to give the power to the field circuit. Substitute all the values and find out the alpha F. So 36.59 degrees. And thank you very much. If you have any doubt, you can ask me directly, or you can ask in the comment box of my YouTube channel, so that I am always available to answer all your doubts.